So now let's further derive this. Okay, so we'll now take a 1D spring, since as I said 1D finite element as a 1D spring. So I'll take 1D spring. Spring is nothing but finite element only. Okay, so I'll take a 1D spring. Okay, since we are talking about finite element, the 1D spring has two nodes, node 1 and node 2. Okay, and k is known for this spring. So we want to find the our quantities of interest are u1 displacement at node 1 and force at node 1. Okay, similarly displacement at node 2, external force at node 2. Okay, okay. So let's try to derive this FEM equations from this. Okay, so can I write F1 something like this? F1 is equal to k u1 minus u2, and F2 is equal to k u2 minus u1. Okay, so what I did, the force at node 1 is nothing but spring constant or stiffness into relative displacement at node 1, or net displacement. Okay, this is nothing but net displacement, right? And similarly at node 2 the net displacement is u2 minus u1, right? uh, just for example, if we'll try to understand this. Okay, okay. If this spring, okay, if it is displaced by 5 mm, and this another node 2 is displaced by 10 mm, okay, the force, internal force which is generated at node 1, okay, generated at node 1 is nothing but the k into net displacement at 1, which is nothing but 5 minus 10, right? Minus 5 k. Similarly displacement at 2 is k into 10 minus 5, 5k. Okay. Mm, right. So if I there is a external force here, okay, the internal force, okay, which is going to act something like this, is nothing but stiffness into net displacement at u1, at node 1. Okay, so we can write u1 is equal to, sorry, f1, and f2 is equal to k 5 minus 10, k 10 minus 5, right? So that means the spring actual compression is 5 mm, right? So we can write something, or if we just want to do check for this, okay, so we can say sigma f is equal to 0, solid mechanics principle. Okay, and we can say f1, okay, plus f2 is equal to 0, right? So we will say f1 is equal to minus f2. Okay, so this is satisfied here. Okay, f1 is equal to minus f2. This is just a double check. Okay, Okay, so we can represent I mean we can write these equations. F1 is equal to K into net displacement F node 1. Similarly, force at node 2 is equal to stiffness into net displacement at node 2. Okay, now I'll let's write these equations in terms of matrix. Okay, so if I write in terms of matrix, f1 f2 vector is equal to k minus k minus k k. Okay, and vector u1 u2, right? So I just did nothing. I just no, write the algebraic equation in terms of matrix algebra. Sorry, I wrote the equations in linear algebra. Okay, and this f1 f2 vector is called force vector. This is called stiffness matrix of 1D element, and this is displacement vector, right? Okay, and if I further write it, okay, we can say f vector for element is equal to stiffness matrix for element and displacement vector for element, right? So you we see that we have got the force displacement relationship. Okay, where k element stiffness matrix. Okay, element stiffness matrix for 1D bar element. Okay, we are talking specifically for bar element 1D. Okay, is nothing but AE by L 1 minus 1 minus 1, 1, right? We have seen this previously. K is nothing but here. K is nothing but AE by L, right? So we can write here AE by L. We can substitute here. Okay, so K effective will get A by L 1 minus 1 minus 1, 1. Okay. So this is our finite element formulation for 1D bar element. And this is what we earlier we said, like we want to find the relationship between force and displacement, and that's what we did. Okay, and so this F, okay, okay, this F vector, force vector is 2 by 1, right? Okay, we were talking about a 1D element, okay, which has two nodes, node 1, node 2. So 1D element, 1D space, right? So the force vector is nothing but 2 by 1 vector. Okay, so so the element degree of freedom of this element, okay, for this element is degree of freedom for each node of that element. Okay, each node. Okay, so if I say total degree of freedom for this element is 2, right? One node has one degree of freedom u1, other node has u2 degree of freedom. So 2 degree of freedom element. Okay, 2 degree of element, d of element. Okay, so for that f is going to be a 2 by 1 vector. K element stiffness matrix is nothing but 2 by 2. So degree of freedom of element. Okay, this one. Similarly, u displacement vector is again 2 by 1 vector. So yeah, so 1 degree of freedom for each node. So 2 degree of freedom element. Okay, so this is a finite element formulation for 1D bar element. F is equal to k into u. Okay, and k is nothing but a by n, 1 minus 1 minus 1 1 stiff matrix, 2 by 2 matrix. Okay, okay. So we have got this FEA formulation, and the small topic is pending, uh, the about the stiffness matrix. Okay. So let's talk about something about stiffness matrix. Okay. K. Okay, so let's see the properties of stiffness matrix. So one property is first property is the stiffness matrix is symmetric matrix. Okay, what does it mean physically? What is the physical significance of this? Uh, that means it has some potential. It has some potential. Okay, uh, or energy. Okay, spring, if we say spring, it has some energy or it has some potential. Okay, the second property is, we'll see this, we'll understand this further. Okay, the determinant of this matrix is always zero. Okay, if you take determinant of matrix no, a by l. Okay, a by l, 1 minus 1 minus 1 1. Okay, determinant, if you take, it's going to be a zero. That means uh, under rigid body transformation, under rigid body transformation, the equation doesn't work. Okay, equation doesn't work. What does it mean? Okay, okay. So equation doesn't work means, the if I mean, under rigid body transformation. Okay, this spring does not store energy. Spring does not store energy. Okay, and if it doesn't store energy, that means it doesn't displace, right? Or it doesn't deform. So under no deformation, spring cannot produce any stresses and strains. Okay, no stresses and strains under rigid body transformation. Okay, so we don't get any stresses and strains. Let's try to understand it with example. Okay, for example, if I take the same 1D finite element, 1D bar element. Okay, okay, and if I say okay, node 1 not 2. Okay, if I apply force F here, okay, let's take it's some 10 Newton. Okay, the external force, okay, F2 is equal to 10, and F1, let's take F1 is equal to 0, external force. We are not applying any force. Okay, so let's try to solve this problem. If I say I know the finite element equations, F1 F2 is equal to K minus K minus K K, okay, and U1 U2. By the way, we can get what is the value of K if, okay, if we know A, E and L. Okay, but let's take K is known for now. Okay, uh, so if I put this loads and boundary conditions in this equation, okay, what do I get? 0 and 10, okay, is, if I say K U1 minus K U2, and another is minus K U1 plus K U2. Okay, that means Ku1 is minus Ku2 is equal to 0, and minus Ku1 plus Ku2 is equal to 10. Okay, so if I just expand this, I will get U1 equal to U2. Okay, and here, okay, if I substitute U1 and U2 here, okay, so what I get, minus Ku1 plus Ku1 is equal to 10. Okay, there is no solution for this. This becomes 0 is equal to 10. Okay, that means we cannot solve this problem. Okay, we cannot solve this problem. Okay, so what we have said earlier, we said that under rigid body transformation this equation doesn't work. Okay, that means spring doesn't store any energy and we don't get any stresses or strains. Okay, so we can say this is a rigid body transformation. Okay, u1 is equal to u2. Okay, and we cannot solve this problem. Okay, and it is very clear, right? If I have this spring, okay, and if I say u1 is equal to u2, let's take 5 mm and 5 mm. Okay, the next configuration, next deform configuration is something like this. Okay, here by 5 mm it is displaced, but the net or deformation of spring is 0, right? Okay, that means spring is simply moving, okay, or displacing by 5 mm, but there is a 0 deformation, and for such cases we don't get any stresses or strains. Okay, by the way, here we know u1 is equal to u2, that means it's a rigid body displacement, but we cannot solve this problem because u1, what is u1 and what is u2, that we cannot find, and that's why we said we cannot solve the problem. Okay, we only know that there is a rigid body displacement, and that's what that is the property of k. Okay, so what we can conclude from this second property? Okay, what do we conclude? Okay, uh, we can say that in order to solve the problem, and in order to get the deformation or stresses and strain, okay, in order to solve the problem, the structure, okay, the structure or element, in this case it's a one element, So structure or element must be constrained. Okay, must be constrained. That means constraint means there is no rigid body displacement, right? For example, if I take now here, okay, if I constrain u node 1, okay, like constraint node 1, u1 will become 0. Now if we take here this one, f2 is equal to ku1 minus ku2. Okay, so if I'll take f2 is equal to k u. So let me just see it again. F2 is equal to minus ku1, or this one, minus ku1 plus ku2, minus ku1 plus ku2. F2 is equal to 10. So 10 is equal to u1 is 0, right? So ku2. So we got the solution. u2 is equal to 10 by k. K is known. Okay, we have just put it k, but k is known. Okay? Stiffness matrix is known. So that means uh, the structure or element must be constrained. Okay? Then only we can solve the problem. Okay, so what I'm trying to say here, okay, since we are talking about just a single element, right? Okay, but if we talk about any structure, okay, let it be random structure. Okay, if we talk about any structure, okay, and if you apply some force at some region, okay, we don't get any solution here. Okay, and see, we are only talking about static problems. Okay, we are not talking any dynamic terms. Okay, we are not talking about inertia forces. We are, so since we are trying to understand FEM through 1D example, we'll go with as simple as possible. For example, 1D example, 1D element, 1D space, we'll go with 1D static, right? So we are talking about the static problem. Okay, so if I apply some force here, this we cannot get solution. Okay, in order to get solution, we must assign some boundary condition. Okay, some constraint, some region should be constrained. Okay, so that is because of the property of stiffness matrix. Okay, generally in any uh, FEA software, if you use, if you don't apply any boundary conditions, you will get the numerical singularities warnings, right? So that is nothing, it is because you have not given any boundary conditions. Okay, so if it is a 3D structure, okay, if it is a 3D structure and in 3D space, okay, xyz coordinate, the structure must be constrained in all 3 degrees of freedom, all 3 degree of freedom, that is xyz. Okay, at any region, okay, at any particular surface, okay, for 3D or line, whatever it is. Okay, so it must be constrained in all 3 degrees of freedom. Okay, it can be anything. For example, this surface can be constrained in xyz. Okay, if that is not the case, if this constraint is a constraint only in x, somewhere else it should be constrained in y, somewhere else it should be constrained in z, but structure should be constrained in all 3 degrees of freedom. Okay, so I'm just giving example. Okay, we cannot give this constraint as per our wish. Okay, it should represent our physical our physics. Okay, physics phenomenon. Okay, I mean real problem definition. Okay, I'm just trying to explain, it should be constrained for the static problems. So that's all for this video. Okay, and we just finished these two properties. Okay, stiff properties of stiffness matrix. And what we did before that, we tried to find the relationship between force and displacement, okay, using spring analogy. Okay, so the takeaway from this is that there should be a force displacement relationship. The structure or the member, if it is represented into equivalent spring, can easily find the force displacement relationship, and we can easily solve the problem. Okay, so that's it for this video. Thank you.